Hey guys! Alright, now we're going to do Chapter 6, Section 2. So yesterday we talked about nth root functions, and today we're going to talk about rational power functions. So you'll notice at the top of your notes, we've got a whole bunch of rules here. Okay, these are the same rules that are listed on that logarithm/exponent properties sheet that hopefully you just got handed. Looks like this guy. Yay. Okay. So the first one we have is called the zero exponent property, and that just says that if you take something to a zero power, it's equal to 1. You know that already, hopefully. Okay, we next have our quotient of powers property, and that says that if you have something to the nth power over something to the nth power, when you're dividing those two things with the same base, you can just subtract their exponents. Okay, we've also got our product of powers. That says if you're multiplying two things with the same base, we can add the powers. Okay, we've got our power of a power, which we talked about yesterday. Okay, that says that if you take something to a power and then to another power, you can multiply those two powers together. We've got our power of a product property. So that says if I take two base numbers to the same power, that's the same thing as taking each base number to the same power and then multiplying them together. Okay, we've got our power of a quotient property. So again, if I take those two bases and I divide them and I'm taking them to the same power, that's like saying the top number to that power over the bottom number to that power. And then you've got your negative exponent theorem. The negative exponent theorem says that if you have a positive x and a real n, okay, then we can say x to the negative n is the same as 1 over x to the positive n. Okay, so essentially if you have that negative exponent, you can just make it positive and move it down to the denominator, and it's the same thing. Alright, graphs of rational power functions. So it says any function with equation f of x equals x to the m over n, where m and n are non-zero integers, is going to be a rational power function. So essentially, this is just like our nth root functions from yesterday, except not only are we taking a root, which is what the denominator of that fraction is going to be, but we're also taking it to a power at the same time, which is what the numerator of that fraction is going to be. So our domain, again, has to be positive numbers because we can't take a root of those negative numbers. Okay, our range is also going to be positive numbers. So let's do some evaluating using these rules. The first one we have is 16 to the 3 halves. Okay, I don't know what this is off the top of my head, but I can figure it out using these rules here. So the first thing I'm going to do is I'm going to say that this is the same thing as 16 to the 1/2 to the 3rd. So what rule did I just use? I used the product of power. Oh, no. I used the power of a power. Okay, use power of power rule. So I use the power of power to split this power up into two separate powers. Now 16 to the 1/2, I know that that's just the square root of 16, which is 4. So this is going to be 4 to the 3rd. This should be memorized. 4 to the 3rd is 64. So I figured that out without a calculator. Alright, my next one is 64 to the negative 2/3. So I'm going to start by using that power of a power property. I'm going to split this up into 64 to the 1/3 to the negative 2. So 64 to the 1/3, that's the cube root of 64, which you should have memorized by now. That's going to be 4. So I can take that 4 to the negative 2. Now, that negative number I don't really like, but remember that using your negative exponent theorem, we can move that down to the denominator and change the sign so that it's positive. So this will be 1 over 4 squared. And I know that 4 squared is just 16. So my answer is 1 over 16. All right, next up, we want to rewrite these expressions without the radical signs. So we're trying to get rid of the radical signs. The first one I have is the cube root of j k to the 5th. Okay, so I know that having the cube root there is the same thing as taking it to the 1/3 power. So I'm going to write jk to the 5th to the 1/3. Then I know that I can use my power of a product property to distribute this 1/3 through. So I'll have j to the 1/3, k to the 5/3. Okay, because if I multiply those 5 and 1/3 together, I get 5/3. So now I have rewritten it without a radical sign. Okay. Next up, I've got the 4th root of a to the 4th, b to the 5th. So first thing I'm going to do, I know that 4th root is the same thing as taking it to the 1/4 power. So I've got a to the 4th, b to the 5th to the 1/4 power. Okay? So now I can use that power of a product property again, and I can distribute these through. So a to the 4th times 1/4, that's just a. And then b to the 5th to the 1/4, that's just going to be b to the 5/4. So my answer is a, b to the 5/4. Okay. Next up, I want to rewrite with a radical sign. So this time they're giving me stuff that is not in radical form, it's in exponential form, and I want to change it to radical form. Okay, so I've got a to the 1/6, b to the 7/6. When I'm changing it back to radical form, I need to think about what would my root be. So with these two, I have the same denominator. My denominator is 6. That means that I'm going to take the 6th root of that. Another way to think about it is using that property that I was using earlier. This would be the same thing as having a b to the 7th to the 1/6. Because then if I distribute that 1/6 through, I get a to the 1/6, b to the 7/6. So since I know that this whole thing is to the 1/6 power, I can write that as the 6th root of ab to the 7th. Okay. Next up, I've got a tricky one. So this one is c to the negative 2/3, b to the 3/4. Alright, so this one's not as easy because I don't have a common denominator, but I can find a common denominator. So between 3 and 4, I know that 12 would be my common denominator, so I'm going to change each of these so that there's something out of 12. So to get here, I had to multiply by 4, so this would be negative 8 out of 12. And then for b, I'd have to multiply by 3, so that would be 9 out of 12. So I can rewrite this as c to the negative 8, b to the 9, to the 1 over 12. Okay. Then I know that since this is to the 1 over 12, that's the same thing as the 12th root. So I've got the 12th root of c to the negative 8, b to the 9. Now, I don't like that negative, so I'm going to use my negative exponent theorem. I'm going to move that to the denominator. So I will have the 12th root of b to the 9th over c to the 8th. Not so bad. Okay. Next up, this is a very long problem, so I apologize. we've got the weight W of a steel ball bearing varies directly as the cube of the bearing's radius, r. According to the formula, W equals 4/3 pi rho r cubed, where rho is the density of steel. The surface area A of the bearing varies directly as the square of its radius because A equals 4 pi r squared. So this is really similar to that problem we did yesterday where we had to talk about volume in terms of the side length, and then we had to talk about side length in terms of the volume. Okay, so first thing we want to do, express the weight W in terms of its surface area. So if I'm going to express W in terms of surface area, I can say W equals 4/3 pi rho r cubed, and I know that A equals 4 pi r squared. So the problem right now is that I can't just plug anything in because I don't know what r is. So what I'm going to do is I'm going to take this A and I'm going to solve for r so that I can plug it into the other equation and get that in terms of A. So I'm going to start by dividing by 4 pi. So I've got A over 4 pi equals r squared. Then to get r by itself, I'm going to take the square root of that, and I get A over 4 pi, and I don't like seeing that radical there, so I'm going to take it to the 1/2 instead. Okay, so there's my r value, A over 4 pi to the 1/2. Now what I can do is I can plug this into this equation for r. So I've got W equals 4/3 pi rho times A over 4 pi to the 1/2, and that whole thing to the 3rd. Now I know that when I take a power to a power, I can just multiply those. So this is going to be 4/3 pi rho A over 4 pi to the 3/2. Okay, so I had it to the 1/2 and then to the 3rd again, so I can multiply those together and get it to the 3/2. All right, and I've got some pi's and stuff in here. I'm just going to leave it in that form. If you guys wanted to simplify it more, you're certainly welcome to. I'm just going to save some time and not do it right now. Okay, the next part says express a bearing's surface area A in terms of its weight W. So now I want A by itself and I want it to be in terms of W. So basically what I'm doing is taking this equation here and solving it for A. Alright, so the first thing I'm going to do is I'm going to divide by all this business here. So I'm going to divide by 4/3 pi rho. So I'll have W over, if I divide by 4/3, that's the same thing as multiplying by 3/4. So I'll just say 3 over 4 here. Okay, and then I'm dividing by pi, and I'm dividing by rho. And that equals A over 4 pi to the 3/2. Now, I need to get that A by itself. So right now I have A to the 3/2. If I want to get it by itself, I'm going to take it to the reciprocal power. So I'm going to take this whole thing to the 2/3. And if I do that to one side, I have to do it to the other side. Okay? So now I've got 3W over 4 pi rho to the 2/3 equals A over 4 pi. Now if I want to get A by itself, I have to multiply by that 4 pi, and I have to do it to both sides. So my final answer is going to be A equals 4 pi times 3w over 4 pi rho to the 2/3. Again, I could simplify it more by combining my pi's and stuff like that, but you guys probably don't want to see it. All right, that is it for section 2.